glasses. You have like 4 glasses plus 4 labs.
And some of them are wet. He made the exam on the same.
Okay, folks, let's go ahead and get started here. So, we're going to be starting on Chapter 14 now. We've actually completed Chapter 13. We've been bang on the schedule all semester long. So, knock on wood, we can keep that up. Okay? Now, this chapter is going to be where we start concentrating on conjugation and aromaticity, and we start adding those factors in. Now, this is kind of interesting because when we have conjugated and aromatic systems, the place that we originally create things like carbocations is not necessarily the only reaction spot, is it? We're going to have it where it starts propagating over. Anybody remember why that is when you have a conjugated or aromatic system?
Because the bonds kind of shift continuously in the ring.
Exactly. You got resonance structures, right?
That's the word.
Yep. You got resonance structures. And that's that where we rearrange the bonds in it and we move the charge, right? So, pretty cool. So this right here is your allele cation. This is probably the example you would remember the best. And this is going to be an example of a conjugated p orbitals and an acyclic pi system. So right here we have a double bond. It's located next to carbocation, right? And that carbocation is going to have an open p orbital and a positive charge. Now, what do we remember about pi bonds? What is a pi bond? It's the double bond. Yeah. Sigma would be the single bond portion. Pi bond would be the double bond portion. And it's composed of p orbitals. And those p orbitals are overlapping and sharing those electrons between, right? Okay. Now, what would happen if you have these p orbitals? They're sharing electrons across the top, right, and across the bottom. What happens if you go ahead and open another spot right next to it? So let's think of that as water, right? Electrons can be very analogous to water in many situations. So we have a nice pond, right? And we go ahead and dig a trench right next to it. Is that trench going to stay empty? No, it's going to fill up, isn't it? Okay. And so we have essentially done that here, haven't we? We have opened up a new spot that's empty right next to this that can very easily overlap, right? It's an empty spot. It's on a single bond, so it can freely rotate. And so it's going to overlap, and the electron density is going to spill on over there. Okay? What is that going to do to the stability of that carbocation? Increase it. What happens when you have more resonance structures in general? Yeah, it makes it more stable, lower energy, right? Okay. This is actually a nice thing to keep in your back of your head. Like, this is why a lot of things happen in biology and inorganic chemistry and organic chemistry and pea chemistry. Increasing the number of places you can be, increasing the number of options, has an entropy effect, which increases the stability, right? This has an even greater effect because we also are increasing how distributed that charge is. Okay? Okay. All right. Now, when we write this as a single structure, these right here would be Kekel structures. They'd be the individual resonance structures for your overall structure, right? When we look at this, are these actually reactions here? No, they're not reactions. What we're really looking at is we can't write this in normal terminology in such a way that makes any sense. Okay? It just is not, right? Has anybody ever seen Da Vinci's Vitruvian Man? It's the one with the arms. Yeah. Why did he do that? Why do people make sculptures like that or make pictures like that? They're explorations of motion in a still frame, right? Okay? And so this is an exploration of something that our current terminology does not necessarily fit perfectly. Okay? So we have resonance structures. We can go ahead and write it as a resonance hybrid. It's a bit more complex of a structure though, isn't it? And so we would make essentially 1.5-ish bonds. You would see the positive charges would be partial positive charges on these carbons here. What about that carbon in the middle? Why doesn't it have positive charge? Yeah, so that one has to be the bridge point, doesn't it? Okay? So like if you have, anybody ever do like the commuting in a city? No? Nobody's ever had to deal with commuting in a city?
I tried.
Nashville, right? Okay, so there's 2 points people want to be, right? They want to be in the city, and then they're done with work or done partying or whatever, and then they go home, right? And so that's the commute point, okay? And so the traffic in the individual parts, the city or the home, not always so bad, right? But where does it always have traffic? Whatever choke point is in between, right? Okay. And so this is your choke point in between, right? So the electrons going between these two spots always have to go through there. Okay? And so it never gets the positive charge because the electrons have to be shared through that. Okay? Okay, so everybody good with that so far? Okay, we're going to be expanding off of that base. That was Organic Chemistry 1 base, right? But review helps. Okay. Please don't forget, by the way, to do homework. We're moving rapidly, and that's true for upper division science courses, right? This specific course happens to be very, very much a chemistry or science of practice, right? Yeah. Okay. So this is right here is going to be your p orbital overlap. This one right here is going to be your pi bond as represented in that original structure. And so what you see is we represent it with this golden pi bond where we're seeing the two orbitals blend together to create one overall orbital structure, right? Okay. Okay. And so this right here is then your empty p orbital. When we have a carbocation, it always ends up with an empty p orbital because we took away the electrons from that, didn't we? Okay, and so what you see here is this is actually the representation of one of the resonance structures right there. Now, the valence bond theory that accounts for features of bonding in individual resonance structures, but we don't account for things like delocalization of the electrons in resonance hybrids in those original models you were taught back in general chemistry. Okay, and so we need to expand on from those. So these are going to be where you have a simultaneous overlap of 3 p orbitals, and that's going to give you your overall resonance structure, right? So we're going to have a simultaneous overlap of these 3 p orbitals. So they're going to be parallel to each other. They're going to be on sequential atoms. These are going to be called conjugated p orbitals, and that's where that terminology conjugated comes from. They're conjoined, right? A set of conjugated p orbitals will represent a single pi system of orbitals. So you can think of it a bit more like instead of having the one contained blending of it, we in fact have a overall contained blend of it. But remember, when we are looking at those blendings, where they're bleeding into each other, they were a system of pi orbitals with anti-pi orbitals, right? Okay. And in this case, if we join 3 p orbitals together, how many orbitals do we have to get out? Okay, if you join together 2 atomic orbitals, you get how many molecular orbitals out? Okay. What's the rule for all of science? If you have something, can you create or destroy? No. What happens to everything in the universe? Just transforms, right? Or gets put somewhere where you forget. But, so if we take orbitals, orbitals are just representations of magnetic fields and electrons, okay? So we can never change the number of orbitals in any structure because we can't change the number of electrons, can we? We can't create or destroy. And so if you put in 3 atomic orbitals, 3 p orbitals, you're going to get out 3 orbitals, right? In this case, 3 molecular orbitals. They're going to be various types of pi orbitals. Okay? And so it'll be a pi orbital system or a pi system of orbitals. Now the electrons are going to occupy a particular pi system. They're going to be delocalized over all the atoms that will contribute to those pi orbitals to that pi system. You can actually best sort of think of them as either a like stream, and so it's like bent along the structure, and the electrons flow along the stream, or a pool, like a wading pool. Or you can think of them a bit more like a wire, okay? So you have like a wire that's circulating these electrons along there, okay? Okay. Now remember, that is above and below. Those are a single pi system, right? Like these two parts were one p orbital right here, okay? Mm-hmm.
The bottom is the anti-pi orbital?
It isn't. Yeah, that's what I'm actually trying to point out here is, like this was the p orbital. When they join together, this is the pi orbital. Both sides, it's just one. Okay. The anti-1 is going to have a different geometry where the electrons, it'll have nodes, and the electrons will not be shared among the different carbons, and they will in fact pull the carbons apart. And that's what makes it an anti-bonding orbital. Bonding orbitals will be shared, and so they pull carbons together. Okay? And they'll have a geometry. They may have nodes. Higher energy bonding orbitals can have nodes. But they'll be in such a way that they're going to be shared between two atoms, and they'll pull the atoms together. Okay? And so you can very easily always identify bonding versus anti-bonding by the fact is, like, are the electrons being shared and get pull things together? Or are they on like the opposite sides of things and trying to pull them apart? Okay. So here's the conjugation stability again. So all the p orbitals in this case are going to be conjugated. This is the more stable configuration. Note, however, because this was a single bond in that other model, right, that theoretically these p orbitals could have been moved around, right? And in fact, before we made a carbocation, this p orbital was almost surely not overlapped with these other ones, right? And so what ends up happening is when you free that p orbital, it's always going to end up rotating to overlap those other p orbitals because that's going to be the most stable configuration, right? Once it gets into that, it's going to be a very hard time to knock it off there, okay? Because this is going to be much, much less stable, right? So for example, is it very easy to go ahead and tip your desk so they're like this? Why doesn't that happen? Gravity. So we have stable and unstable configurations of our desks, right? Okay. And the reason your desk isn't like this is because that's an unstable configuration, right? Stable configurations would have it up or down. One of the two, right? Okay. And we're seeing the same thing here. This unstable configuration, stable configuration. You're not going to see this one for any give it really length of time. You could see this happening actually, where it is overlapped. It comes out of overlap and then quickly snaps back in and becomes overlapped again. Okay? Okay. But again, that would require quite a bit of energy in the system to happen. All right, so let's talk about rules of resonance to identify pi systems and pi electrons. In a resonance hybrid, each atom over which the electrons are delocalized contributes a p orbital to the same pi system. Let me ask you a question. So I want to make a new stream, new tributary to the local river, okay? If I dig right here, outside the window, am I getting a new stream? No. Why is that? Distance, right? Limestone? Did you say? I'm not close to the river, am I? So, like, water can't flow in. Okay? So, if you have a conjugate system, they have to be close together, right? The p orbitals have to be adjacent to each other. Okay? Now, you do have a bit of a thing that students have a difficulty kind of getting at first, and that is that what if I have 2 pi bonds that are on the same carbon? Is that possible? Yes. Yeah, we could have a double bond and then another double bond on the same carbon, right? But can they occupy the same space? No. And so what happens is one ends up like this, coming in and out towards you, right? The other ends up above and below, doesn't it? Would those systems be conjugated? No, they don't have overlap, do they? Yeah, one's coming out towards you, one's going above, isn't it? So they don't actually overlap at all, do they? Okay? And so this is the place where people actually have the most difficulties with this, is that they get tripped up with the fact that you have like 2 pi bonds, okay, 2 double bonds, and they overlap on the same carbon. They have to not overlap on the same carbon. They have to be adjacent to each other, right? Okay. They can't be 1, 3. They can't be 1, 1, right? Okay. They have to be 1, 2 next to each other. Okay, so the number of electrons in a pi system is going to be the same as the number of electrons delocalized in its resonance hybrids. Remember, you can never create or destroy right. I say this lots and lots because it's by far and away the most common mistakes people make and have difficulties with. We're just not computers, and we don't keep track of every single thing, right? You can count the electrons by interconverting resonance structures in such a way that all the atoms that contribute p orbitals to the pi system are involved. Okay. So which of the atoms in the hexa 1,3 diennyl cation contribute p orbitals to the same pi system? How many electrons are in the pi system? Now again, I'm going to point out that a useful analogy in your head is thinking about this as a water body, like a pond. And you're opening a little tributary of it, right? You're opening a little stream to it. Okay? Okay. And so which of these would be involved in this conjugated system? Okay. I'm going to start with the double bond here. Okay. Because conjugated involves double bonds, right? Okay. It doesn't actually involve, like, cations and carbocations are not actually conjugated if they have nothing else. That's why we didn't talk about it with a number of the carbocations we made in like SN1 reactions, right? Never came up. Because a single carbocation, not conjugated. 2 carbocations, not conjugated. Don't have any electrons. Okay? No water to share. All right. This one. Is this a conjugated system in the first place? Yes. We have 2 double bonds here that can share electron density, right? And they are next to each other. So those are going to be adjoined. Okay, they can have electrons flow from one to the other, right? Another way of saying that is there's a p orbital here, they can blend together, right? Okay, so is this carbon going to have a p orbital that's contributing to a pi bond? Yes. And so that means that one has to be part of that conjugated system, doesn't it? Okay. How about that one? That one as well. How about this one? Yeah. This one? How about this one? Ooh, does it have a free p orbital that could overlap and let electrons spill into it now? It does, doesn't it? And so this one is also part of that conjugated system now. Okay? Back when it had a hydrogen on it, it was not. Right? Or a bromo or whatever the hell it had. Right? It is now, though. Okay? Because it has an open p orbital, those electrons in this conjugated system can spill over. Okay. Is this one part of the conjugated system? No. No free p orbital to let electrons spill in, right? Okay. Okay. And see how it kind of can be like useful to think of it as like a stream bed, right? So we have our stream here. This one's part of the stream, part of the stream. We're joined to the stream, so still want part of it, right? This is still part of the water body. And then we dug out this one, didn't we? And so now that's part of that water body. Okay? Okay, what if there was no carbocation here and there was one here instead? Would these be part of that conjugated system anymore? No, they would not, would they? Yeah. Exactly. Exactly. We can't jump over this, can we? Yeah. Yeah. How about if they're both carbocations through some magic? Yeah. Theoretically, you could, yes, make the whole thing conjugate that way. Okay? You couldn't actually get these two to be carbocations and keep the molecule actually together. But in theory, okay, you just need to have open p orbitals that could overlap so that the electron density flows into them and can flow back. Okay, you'll never see anything like that, so it'll never be an issue. Okay, all right. And so this right here is actually what this partial positive charge looks like and does. And so these would be the individual resonance structures here. And so what we can see here is that we have our carbocation, that's the original structure, right? And this would be have a resonance structure where this double bond goes over here and has the carbocation right there. So in terms of which ones would be reactive carbons and could have substitutions, the possibilities would be this carbocation right here, this one, and this one at the end. Those would be your possibilities. Energetically, it's more favorable to do substitutions on this one and this one. Could anybody tell me why? This is the critical thinking portion of the class, by the way. Please try to answer it in your own head and don't wait for me.
Less substitution.
Hmm?
Like less sterically hindered.
So that won't be the biggest factor in this case. And it probably would have more positive charge for this one because it's more stable there. The big factor here that's going to kill this one's reactivity is if you do substitute this, you no longer have a conjugated system. So you would have destroyed your conjugated system if you do this. Okay? These are both conjugated systems, even when you put a hydrogen or whatever on. Okay? And so that means those are just more stable systems, right? Lower energy systems. Okay? Okay. All right, this is what it would look like with the conjoined p orbitals for that overall structure. Does anybody have any questions about this? No. Mm-hmm.
That's 4 electrons there, man. I see it.
Mm-hmm.
Pi system contains 4 electrons.
It does. 2 for each of the pi bonds.
And then the carbocation doesn't contribute any.
No,
It's empty.
it's empty. Yeah. Yeah. That's why it's the free p orbital. Now, an interesting factor is like, we'll get into more of these complications and things as we go. But for example, any p orbital they can have electrons flow into or could join together would work. Okay? So if you have a p orbital, it's not a hybrid orbital, sp3, sp2, that sort of stuff, they'll work. Okay? So for example, if you're starting to make connections, you guys actually know a bunch of these already. Like free radicals we had talked about. Free radicals can do things like this. Okay? Carbines could do things like this. Right? Yeah. So you can actually make a ton of connections in this class now. We actually have like the building blocks we're going to be using for everything already. At this point, the only thing we're missing is the spectroscopies for your base building blocks. Okay? All right, so this right here is what this would look like in terms of geometry. This is what these conjugated systems look like. So keep in mind that when we're talking about conjugated systems, they have these big pi orbitals above and below, right? And so that means that those things are always planar, aren't they? Okay? Or they're always planar, right? And so if you conjoin those together, what ends up happening to your geometry? The whole thing ends up planar, right? Yeah. If If you stack a bunch of wood pieces next to each other, they still end up planar, don't they? They don't magically like do curving. And so what we see here is we always end up with these planar structures. As long as it's conjugated, the whole thing will be planar all the way through. Okay, single plane. The distances are kind of interesting. So what you actually end up seeing is that the single and double bonds actually sort of blend in terms of distance. Okay, so instead of having a single bond that's 154 picometers, the single bond, that's actually not really a single bond, right, is actually 135.4 picometers. The double bond here ends up a little bit longer at 133.8 picometers. Because remember, it's no longer only sharing that electron density between those, right? Now you do see it's not an average of the two, and so they're not really 1.5 bonds. Something we say to make it easy to remember. But in reality, this conjugated system's more stable than a double singles, right? And so it actually tightens up the whole system. And they all end up being stronger bonds. They all end up being a little bit shorter. Okay? Because it's just more stable overall. Stronger system overall. All right? Okay. Does anybody have any questions in geometry? Okay. Now that does mean you can do some very crazy, interesting stuff and make these very planar structures, which you don't see a lot in like normal everyday things, right? Okay. Okay. Anybody know of a conjugated system that you guys have in this room right now? No? Anybody ever heard of allotropes? No, yeah? Was it from me they heard of allotropes? Okay. Okay, cool. So allotropes are different forms of a substance that are just different in their structure. Okay? So for example, carbon has several allotropes. There's charcoal, coal, right? There's diamonds, and then there is graphene or graphite, which is your pencils, right? And the form that's in your pencils, the graphite, when you layer out single layers, that's graphene, is actually a conjugated system. Okay? They're conjugated systems that layer on top of each other and stick. So when you draw with them, you're actually rubbing off layers of graphene on your paper. Anybody heard of like carbon nanotubes? Yeah? Those are layers of graphene that you take and roll up into a tube. The individual graphene layers are super strong. The layered on top of each other are not very strong because they're just very large dispersion forces. Okay, so these are the conjugated p orbitals in buta-1,3-diene. Can everybody see that okay? Okay, and so what we see here is we have 4 pi electrons in this system. They're going to be delocalized over those 4 carbons. And this system is going to be composed of how many orbitals? 4, yeah. 4 p orbitals went in, 4 pi orbitals come out. Okay? Okay. And so when we start looking at isolated pi systems, so this is 2 different isolated pi systems. We have a double bond right here, which is a pi system, right? Only has 2 carbons in it. And then this one over here is another double bond, but has a carbocation next to it, right? And so this is a 3-carbon pi system, isn't it? Okay, or conjugated system. Now, these ones here, why can these not come over and blend together? Yeah, these dang tetrahedral carbons, right? Okay. Okay, so we have a desk, and then I put, you guys ever seen tank traps? A tank trap? Caltrop? Any ever seen either of those? Yeah, caltrop. Mm-hmm. Yeah, they're tetrahedral in shape, right? Yeah, and so it's something you should be able to easily view at your size. And everybody's seen World War II pictures because, like, if they're going to teach you history, they're going to teach you some World War II in the U.S. Hey. So, yeah, those are the tetrahedral, large steel structures that you saw on beaches of Normandy and stuff. Yeah. Those are tank traps. They're the exact same structure as a caltrop because they have the exact same purpose, right? To not allow a vehicle or a horse to go across them. Okay? Now, they're a very stable structure in three-dimensional space, as we have seen many, many times in organic chemistry, right? And so if you have a flat thing, then you have a caltrop, then you have another flat surface. Is it easy to go through to another flat surface? No, in fact, that's the whole purpose of a caltrop or a tank trap, right? Makes it really hard to go the other side, doesn't it? Okay? And so what we're seeing here is that these are these sp3 hybridized orbitals, right? They have a completely different geometry than our p orbitals. Okay? And so they have absolutely no possibility of overlapping and allowing electrons to flow through them, do they? No. And so that's what ends up happening. You're essentially throwing a three-dimensional structure that has no possibility of actually overlapping and allow electrons to flow through. Okay? Okay. Now, an interesting little factoid of this is if there was an energetic favorability, we could do some hydride shifting, right? But that's a reaction, okay? That's not a resonance structure, right? And that's what we're talking about right now, is resonance structures. Okay, now this is again your two pi systems. Is everybody okay with those and why you can isolate those? Okay, yeah. So these don't allow them to blend. All right, so this right here is going to be an example of an increasing stability due to that conjugation and why one position becomes more reactive and more stable versus another. So right here, we have a benzene ring. It's next to a double bond. And so what we can actually see is we could do a reaction here where we do an elimination, right? So we add some base. This is going to deprotonate one of these positions, isn't it? Okay. Which position is it going to want to deprotonate, and where would we likely get the double bond? How could we choose between those? Okay, let me take a step back because some of you are looking at me like, what's an elimination? Okay, so if you remember from the first semester, the four major reactions that we really concentrated on and we're always running together and we concentrated on why one happens over the other was E1, E2, SN1, SN2, right? Okay. The E1 and E2s were eliminations, okay? And they happen from, E1 happens from leaving group leaves, and then you get the base taking a proton off, right? E2s happen because you have a strong base, like we have here, and it pulled one of the protons that was adjacent, called the alpha proton, off. And then that caused the electrons to then go over, form a double bond, and then the leaving group left, right? Okay. Now there's two options for here. There's two alpha carbons here and here, right? And these products here represent those two options. So this forms the double bond, which would be right there, right? This one forms the double bond on the other side, which would be this one. Okay. Now, which one would be more stable and thus more likely to be the one that forms, i.e. your major product? Conjugated, the one that's a conjugated system, right? Which one has a conjugated system then? Yeah, the one that's right next to it, right? Now, you could actually call this alpha conjugation, by the way. It's another terminology for this. It's kind of fallen out of favor as, in general, IUPAC doesn't like alpha, beta, gamma. Biology really still likes those. Anybody ever heard of a gamma or omega fatty acid? So you can have beta, you can have gamma, and you can have omega fatty acids. Omega fatty acid probably being the most famous, right? Okay. Okay. Those are actually the Greek alphabet away from your endpoint. Okay, so let's look at some more separated pi systems. This is going to be a triple bond. So when we have a triple bond, what is a triple bond? Yeah, we have two pi bonding systems on the same carbons, right? So we have one of them that's above and below, one of them that's coming out towards you and away from you, right? And so, of course, triple bonds can overlap with other pi bonding systems, okay? In fact, if there is a pi bonding system next to it, it for sure will overlap with it, okay? Because it has both directions that can do, right? Lots of options. All right, so this right here is going to be an example where we have the triple bond here that's going to form part of this pi bonding system here. Okay, it's going to include a carbocation, a double bond, and one of the pi bonds from this triple bond, right? The one that overlaps, which is above and below, let's say. Okay. Now, this would be the actual resonance structure of that. Isn't that kind of interesting looking? Ooh, You don't see a positive charge on a double bond very often, do you? No. But remember that positive charge is that conjugated system on top, right? The double bond is actually on the towards you and away from you. Okay? They're not actually overlapped right here. All right, this is actually what it would look like. Again, see the conjugated system on top and below. And again, we have the ones coming out at you, which would be that triple bond one, right? Okay. So the heat of hydrogenation, this is delta H naught, hyd for hydrogenation, excuse me. This is the enthalpy change that's going to accompany the addition of H2 to an unsaturated species. This is essentially the energy of those pi bonds, right? That's the best measure we can do of what those energies of those pi bonds would be. Okay? And so when we hydrogenate something like a conjugated double bond, we would hydrogenate the whole thing right here. And what we would see is we'd have a negative 221 kilojoules per mole. So that releases some energy, and that energy is negative 221, right? Okay. When we do this to an isolated system of double bonds, what we would find is that would actually release 241 kilojoules per mole. Why is that more energy that gets released?
Just conjugated, just more stable.
Exactly. Yeah. This was a lower energy system, right? So we didn't have as much energy to release. Okay? And so, yeah. This is actually the stability difference, isn't it? Conjugation for this system, that difference is 20 kilojoules per mole of energy. That's how much more stable it is. Okay? Isn't that nice? We have a very easy way to compare these things that we can directly measure in a reaction. So, very convenient. So here we see, we go ahead and put these on order stability. We have very specific energy values for this one because we have a direct reaction we can go ahead and just measure the energy for. Okay? Very, very, very convenient. So what you see here is if we have a conjugation of those double bonds, that's going to give us 20 kilojoules per mole more stable than if they were separated, right? If we start looking at those in terms of the single bonds, what we can see is if the single bonds were on two different of the same sort of compound, what you would actually get is that would have the same energy as if they were separated. Okay? So, for example, if you were to hydrogenate these two compounds, you'd get the same amount of energy out. All right? This is not more stable or less stable than this in a particular meaningful amount. Okay? There'd be a little bit of difference, but nothing that, matters. Okay. And so this right here would be no stabilization effect. This is two different systems. Again, if they're isolated on different compounds, it doesn't really matter because they're still isolated, right? The degree of isolation doesn't really matter much. Everybody okay with that? Any questions there? Okay, so we're comfortable with carbocations being part of conjugated systems now, right? Okay. Now we're going to spread the conjugated system love over to all of the other things we've talked about. Okay? And a lot of it's going to be highly related. So don't try to memorize every single thing as individual things. Please understand the pattern. Okay? It will really reduce your load for your studying. All right, so this again is going to be an allyl anion. So this is where we'll have an anion that is next to a pi system. Okay? And notice that when you have an anion, what happens to those electrons? They go into a p orbital, don't they? Yeah. And so we have a p orbital. It can overlap with our pi system. This will then share those electrons with the rest of the pi system. And that's going to give us a distribution of those electrons over the entire structure. So instead of partial positive charges, we get partial negative charges, right? Mm-hmm.
So would this be making carbanion or carbene?
So carbene is the no charge.
Okay.
And we're actually missing 2 electrons there, but we don't have something that's actually pulling the electrons off. We just haven't made 2 bonds. This is a carbanion. Yeah. And that has a negative charge, and it has a p orbital that's full, and another p orbital. This will not have the extra p orbital that a carbene would have.
Okay.
Yeah. So a carbene would actually have 1 p orbital that's full, 1's empty. Okay. And so in this case, what we're going to have is an overlap of that p orbital. It's then going to flow into this conjugated system, and so we have a 3-carbon conjugate system again. Okay? And you can see it's very analogous to the carbocation, right? Instead of positive charge, negative charge. Okay? Okay. The big difference here, and the thing you gotta watch out for in terms of like, I have 2 electrons, they're in a lone pair, is do those hybridize? Okay? If the orbital's in a p orbital, it can overlap. If it's hybridized, if it can hybridize, it's not going to overlap. Okay? And that's the big thing you have to watch out for here. Okay, so this is going to be a acetylide enolate formation. This is the acetaldehyde to the enolate anion. And so what we see here is, remember how like when we had a double bond next to an alcohol, and we had it in the presence of like a base, it did that tautomerization. We called that the enolate tautomerization. Okay, that's this. And so we have an acetaldehyde right here. This right here is the double bond. This would be an alcohol. It's lost its proton, right? Okay. Okay, or an enolate. And so this is actually that resonance structure that develops between these, and that's where we get this resonance hybrid right here. And note that this is what it's going to look like. This right here is the oxygen. That's why it has this lone pair set right there. Okay. Notice this set of lone pairs here, that right there, those are hybridized, aren't they? Can you see how they're in that trigonal planar structure that you would have if they were like hydrogens or something? Okay. Those are hybridized. It's a trigonal planar structure for those lone pairs there. Okay? And so those lone pairs don't have any ability to overlap here and get pulled into these. Okay. Again, we have a 3-atom system for our pi system that's contributing electrons to this. The number of electrons in this would be 1 extra than it would normally be. Or another way of saying that is it's 2 more than our carbocations were. Okay. All right, this right here is benzene. Benzene's cool, and the reason we had some interesting chemistry of benzene is because it is a ring-wide conjugated system, right? So the whole ring is conjugated, and it's planar for the whole ring because it has a continuous p orbital system that is the entire ring. It looks like a donut. Can everybody see the donut? Okay. Anybody else not have breakfast? Okay. Okay. Yeah. Yeah. I could really use a donut. All right. Actually, X that. I could really not use a donut. All right. So this is the resonance system right here. You see, you just do the rotation of the bonds there. And these are the two resonance structures. This is the overall representation you'll oftentimes see. Please note that they oftentimes write this like this. Like so. Okay? That means the same thing. All right. Does anybody have any questions there? Okay. Now, the distances in these bonds, they're all the exact same. There's no difference in them. They're symmetric. And so they all end up with the exact same distances. You notice in the previous structures, we had slight differences in the distances, right? And that's because they were different. Some of them were at the end of the conjugated system. Some of them were in the middle of conjugated systems. And so you got slight differences. Okay? This one, there is no end of the conjugated system because it's a circle, right? So they're all the same. Benzene's systems of pi electrons is unusually stable because it makes a full circuit. We call this aromaticity. It is very, very tangentially related to it being like aromatic as in smell. Okay, the English word smell. Okay. So don't think that like all aromatic systems have a lot of smell and that's a thing. Okay. It's a very common misconception. Okay, so like if we do normal reactions that would work on conjugated systems, right here we have a conjugated system. It has this double bond, this double bond, this double bond, forming the conjugate system, right? We can do a bromine addition across that double bond in the middle, and we'll get 75% yield, no problem, excellent. Just like we saw in the previous work, right? If we try that on a benzene system, we will not get any reaction. It really doesn't matter how long you let this go or try to do temperatures. You're going to burn the benzene before you could possibly get this. Okay? You'll evaporate or burn benzene before you do it. So it really doesn't matter. Why would that be that we can do this reaction, but we can't do this one? They have the same number of conjugations. See that? Same number of double bonds, right? So what is like the easy answer if you have a question in chemistry? It probably is the answer to everything. You just have to figure out why it's the answer to everything. Stability. Yeah. It's more stable, right? So benzene is more stable than this system right here, and so it's much higher energy to do this. Now you can actually do this in a different manner, which is that you can take one of the hydrogens off of one of those carbons and then not break the conjugated system and then add or swap a bromine in. Okay? So this is a reaction that would accomplish adding a bromine to benzene, but notice you do not break the conjugated system. Okay? Breaking that conjugated system is very, very high energy, especially if you try to do it permanently. Okay? All right, so cyclobutadiene system of pi electrons is actually unusually unstable. What in the world? Wait a second. Come on, you should be just going, what the hell, Dr. Clausen? We have a ring here. We have double bonds in it. It's conjugated. That's stable, right?
Yeah.
And then you go on and 4-membered ring all of a sudden instead of 6-membered ring, and we're not stable anymore. What are you doing to us? So it matters on the order stability, how the pi bonds are made, right? So when we put in orbitals, okay, when we put in orbitals, what do we have to always get out? The same number of orbitals, right? And those orbitals are going to be a mixture of bonding and anti-bonding orbitals, right? So what ends up determining the stability of these structures is how your electrons fill in. If they fill in all bonding orbitals and no anti-bonding orbitals, then it's going to be very stable, right? But if you start filling in anti-bonding orbitals, what's going to happen? Okay. Anybody ever play any sort of sport that requires you to have weight on you? Football is a good example. The wrestlers usually wear those weighted things or packs. Okay, or have you went hiking? Okay, so whenever you have weight on you, if you distribute that weight very well, you can be highly stable, right? And you feel a lot less of that weight. But what happens if you concentrate all that weight in one area? It starts pulling you off balance, right? Okay. And the same thing happens with orbitals. So if you put electrons that are between atoms and are going to pull atoms together, it's going to make it very stable, right? And it's going to hold it nicely together, okay? But what if you start putting electrons away so it only attracts one of the atoms and it doesn't attract the other? That's going to start pulling things apart, isn't it? And that would be putting electrons in anti-bonding orbitals. Those are anti-bonding orbitals, okay? They're like a poorly packed backpack. Pulls you right over, and then you fall, right? Okay, so this right here is actually the cyclobutadiene's measurements. We can see the double bond is 132 picometers. We have 160 picometers for this bond. Wait a second. What measurements are single bonds usually? Like 154-ish, right? It's longer than a normal single bond. What does that tell you about that bond? It's not held together, right? It's held together less. It's a weaker bond, okay? This is actually your resonance structure right here. These are not resonance structures here. They're actually not going to resonate. And that's because they have different bond lengths right here. And so you actually have what are referred to as nodes here. You can't actually have the electrons flow freely among these different structures. This is, in fact, an equilibrium here. So you're actually breaking and reforming bonds to make these. Okay? And that does happen in most room temperature systems if you have this. You won't have this very long, though. Because it is unstable. Yeah. By the way, this is actually something that's formed fairly often and can be quite dangerous to deal with because these make a lot of different products very quickly, and people don't look up the possible products they make, and one of them actually destroys your immune system and absorbs right through rubber gloves. Yeah, it actually killed 2 graduate students at the University of California because they were doing a similar reaction where they're cracking a compound to get these. And then they looked up this, they looked up the compound they were using, they didn't look up the reaction. And so they handled the compound as they should not have. They put on multiple layers of gloves and tried to clean it up with paper towels. Yeah. And that was not what you should have done. Yeah. Anyways, so one of the things to keep in mind is if you're ever working with something, always make sure you actually look up all the layers. Don't just look up what you put in. Okay? Okay. So this is not the resonance structure here. Okay? So benzene is classified as aromatic. Cyclobutadiene is actually anti-aromatic. It's the opposite of aromaticity. Okay? It does not share a conjugated system along the entire ring structure, and in fact gets a destructive feedback that makes it less stable. Okay? Aromatic compounds are going to have cyclic pi systems that are going to be unusually stable. Anti-aromatic compounds will have cyclic pi systems that are usually unstable. non-usually reactive. And so anti, again, is used in the sense of it's the exact opposite. Okay? All other compounds will be classified as non-aromatic, i.e. they're neither of those. They're not unusually stable, not unusually unstable. They're just not. Okay? So is everybody okay with that terminology? Okay, let's try it real quick. Okay, benzene is? Okay, butadiene is? A 6-member ring with 2 double bonds in it is? Non-aromatic. Yeah, it doesn't have an overall system of pi bonds for the whole ring. Okay? Okay. So just not. All right. So let's go ahead and use the heats of hydrogenation real quick, and we can look at aromaticity. So if we do benzene and we were to hydrogenate it, this actually takes really, really harsh conditions. So you have to put this in with catalyst. You have to put this at high pressure. You actually have to pressurize the system. And you have to put it at high temperature. Anybody know why you'd have to both high temperature and high pressure?
It excites the atoms and gets them moving around.
Exactly. You can use pressure just like temperature. It'll effectively increase concentration, right? And they'll bang into each other more. And you use this because, can you just raise temperature on things all the time? Yeah, could I like put this in a blast furnace? A few thousand degrees? No, it's going to burn, right? I'm not going to have anything benzene related at the end of this. I'll have CO2. That's it. Okay? Can I just like put it in a star? Whoop. No. No, there's limits, right? That would actually cause fusion. Yeah. I wouldn't even have carbon at the end of this. So this right here, the heat of hydrogenation for benzene, we get negative 206 kilojoules per mole. Notice that's 3 bonds that we just did, and it's only negative 206 kilojoules per mole, right? That's really, really, really low. That's way lower than our other examples we've looked at, because we've normally been looking at single double bonds, right? This right here is 3 cyclohexenes. So if we did this, the 3 cyclohexenes, what we would see is that's negative 356 kilojoules per mole. Look at that difference. 150 kilojoules per mole in stability. Mm-hmm.
So I'm just confused. Is that saying it's taking in that energy to do it, or it's releasing?
No, it's releasing.
Okay.
Yeah. It's still more stable to have all single bonds. Yeah. Sigma bonds are the most stable, because you're sharing electrons between 2 atoms directly, rather than having it way up here where it's loosely associated and they're delocalized, right?
Okay.
Yeah. So when you look at single bonds, sigma bonds are basically always more stable than double bonds. Okay, and that's why, remember those trends like 2 single bonds is twice this stability. Usually it's like 75% of the stability for a double bond, as 2 single bonds would be. Okay? And so, yeah, single bonds always more stable. The overall thermodynamically, this would give off energy basically always. Okay? Maybe if you start getting enough benzene rings and enough stuff going on, maybe you could start seeing something, but no, single bonds are more stable. Okay? Now, in terms of the intermediate stuff and kinetics, this is going to be very, very difficult of a reaction to do. Okay? So, like, for example, you could actually do this reaction under lower temperature conditions, as long as you had enough temperature for the reaction to go over the activation energy at all. But it would take years. Yeah. That's actually that next reaction we're going to do. After this experiment 17, that 54, that's why it's an hour and a half of heating. Because it's going to be a benzene system, an aromatic system, and it just takes we're playing catalyst tricks and everything, and we're still going to take forever to do. Okay? So we'll get it started, and we'll do everything else and work on 17 while we're doing that. Okay? Yeah. Okay. Anybody have any other questions on this? Okay. This is the stabilization by aromaticity for these different compounds. So right here we see benzene versus 3 rings with a double bond in it, and we see that's significantly more stable, right? And then we see an anti-aromatic system right here, which is butadiene, and we see that's much less stable than it would be just having 4-membered rings with the double bond. Just in case you're wondering, like, hey, 4-membered rings are not very stable in the first place. What sort of difference is there? A lot, actually, right? 400 kilojoules per mole versus 259 kilojoules per mole. Okay? So it's actually much less stable, being anti-aromatic. Okay. All right, and so this is the butadiene's instability when you do the hydrogenation. Again, that's just the same number as we saw before, just so you can understand which reaction does what. So if a species possesses a pi system consisting of p orbitals that are fully conjugated around a ring, then the species is going to be aromatic if the cyclic pi system contains an odd number of pairs of electrons. These numbers of electrons are going to be called Huckel numbers. Anti-aromatic is going to be when the cyclic pi system contains an even number of pairs of electrons. So for example, benzene has how many pairs of electrons? How many double bonds does it have? 3, yeah. If it's all double bonds, then that's a really easy answer, because each double bond has 2 electrons in it, right? Okay. If it's not all double bonds, then you gotta think about what it is, right? Like a carbocation doesn't add any. Okay. Anti-aromatic is when it's an even number, and so when we looked at butadiene, how many double bonds was there? 2, right? And that's an even number. Okay. All other species are going to be non-aromatic, and so you don't have to worry about them in terms of this. You know, the funny thing is the wasp doesn't distract me, but all of you, like, it looks like a wave. And I'm like, oh my goodness, my students. So, yeah, this room's really bad. So for the p orbital, atomic orbitals to be fully conjugated around a ring, the atoms that contribute to the orbitals must lie entirely in the same plane, and we have to have a planar structure. So for each Huckel number that contains an odd number of pairs, i.e. 3 pairs being 6 electrons being benzene, right? Each anti-Huckel number contains an even number of pairs. So that's going to be 2 pairs like the butadiene we talked about. That's 4 electrons, right? Okay. The Huckel numbers correspond to 4n plus 2, where n is any integer that's greater than 0 or equal to 0. And the anti-Huckel numbers correspond to 4n. So n is any integer that's greater than or equal to 1. Okay? So if theoretically you had, let's say we have an n here that's 5. Okay? Okay. So if our numbers of electrons were 4 times 5 plus 2, that would be a Huckel number. That would correspond to this right here, odd numbers of pairs, which would be aromatic. If we had a 4n set, so 4 electrons like we talked about before, right? What if we had 8 electrons? Which one would that be? Anti. If we have 10, aromatic, right? So 4n plus 2 would give you 2 times 4 is 8, plus 2 is 10, right? 10 electrons is an aromatic system. Okay. What if we have 12? Mm-hmm. Got it. Yeah. That's 4 times 3, right? What about 11? Non-aromatic, yeah. Yeah, you couldn't actually form complete aromaticity then. Okay? All right. And so this is your benzene versus cyclobutadiene again, and you can see here the count up of electrons right there. Okay. All right. Notice this is actually the hexatriene, and this would have that same number of electrons as here. And so that's just conjugated. Okay, so let's go ahead and use do some rules for resonance to help predict our aromaticity if we're doing it graphically. Okay, so we're going to draw curved arrows to represent electron movement via resonance. We'll determine whether the species has cyclic pi system, and then we'll count the number of pi electrons so we can figure out aromatic or anti-aromatic or non-aromatic. Okay, if it followed all the other rules. And still doesn't land on one of the Huckel numbers. Okay. So this right here, benzene, we go through step 1, and so we move all of them over one step along that ring, going around the ring, right? And then we go to step 2, and we see that all 6 atoms of the ring are going to be involved. This is going to be a planar ring thus, and we have a pi system that is cyclic, and so it fulfills the condition so far. And then we get to step 3, and we see that we're moving 2 electrons in each of these ones. And so that is 6 electrons, right? That's a 4n plus 2. And so that one's aromatic. Okay. This one right here is going to be the cyclic butadiene. So what we see here is, again, maximum movement involves the entire ring here. And it's depicted by these curved arrows again. And so we have the entire ring. It is planar. And it is a pi system that is cyclic. So we're good so far. We get down to the number, and this is 2, 4, right? And so that is a 4n, isn't it? And so that is then anti-aromatic, isn't it? Okay. We go over here, and so we do maximum electron movement again, representing those arrows. And we see that we have all 6 atoms are involved, so we are planar, right? But doesn't come back around, so it's not a ring, is it? Okay? And so this doesn't have any aromaticity. It's non-aromatic. We just stop there. We don't have to worry about Huckel numbers because not any form of aromaticity, right? Yay, we have one less step. Never a bad thing, right? We'll go ahead and do the rest of the exam. Well, we have one more minute. Let's try pyridine. Or I'll have you look at pyridine. You can have nightmares about this, and then we'll talk about it. It's a whole, like almost a week, isn't it? Ugh. Your weekend will be ruined because you'll never know. You'll have dreams.
I'm sure it's aromatic. If not,
You all have a wonderful time. I'll see you on Friday. We'll have some fun.